Every year, new drugs hit the market with the hope of tackling these issues. In modern biotechnology, scientists are tasked with solving widespread health complications, such as heart disease, Alzheimer's, and cancer. Every year, new drugs hit the market with the hope of tackling these issues, so we can live longer and healthier lives. The research that goes into the development of therapeutic solutions requires a well-exercised foundation of physics and biology. The manipulation of lasers, sensors, and computers creates valuable insight into the world of molecular biology, with many techniques offering their own pros and cons. One of these techniques is called fluorescence and anisotropy. But before we get there, here's a quick refresher on how fluorescence works. You may be familiar with a process called luminescence, which is when a substance emits light without the use of heat. Quick refresher. Fluorescence is a type of luminescence that you can find happening in certain jellyfish, cosmetic makeups, highlighter pens, and it is even used in sutures to help surgeons see better. Let's take a closer look. Fluorescence happens when a ground state singlet absorbs a photon and temporarily increases its energy state. At this point, it's possible that the electron will experience non-radiative loss of energy in the form of vibrational energy, but this is not fluorescence. After absorbing the photon, the electron is less stable at its higher energy state and will drop back down to a lower orbital. To do so, it will spontaneously emit a photon, and this is where fluorescence occurs. Quick reminder, this entire process is just one of many ways an excited electron can transfer energy to go back to the most thermodynamically stable state. We still have phosphorescence, pair formation, and other types of scattering that won't be covered in this video. We understand how fluorescence works. So what exactly is fluorescence and anisotropy? With respect to biophysics, the entire process is just to measure how well two molecules bind to each other. The experiment goes something like this. You take a laser and shine it through a filter. That light is now plane polarized. There are at least two molecules that can interact with each other. One is the fluorophore, and the other forms a chemical bond with it. As their chemical bond brings them closer and closer, their angular momenta combine, and that's what we're looking for. Shine that polarized laser light at the fluorophore, and emission begins. Pass it through another filter, we take our measurements from a detector, and we're done. That's the basic rundown, but we can do better. Let's rewind and take a closer look at things. The reason for that first filter? Light actually travels in a wave along an axis. However, it's not so straightforward. Millions of and emission begins. Pass it through another filter, we take our measurements from a detector, and we're done. That's the basic rundown, but we can do better. Let's rewind and take a closer look at things. The reason for that first filter? Light actually travels in a wave along an axis. However, it's not so straightforward. Millions of photons are being emitted over a few seconds, and they are randomly oriented. The filter is polyvinyl alcohol plastic, doped with iodine, stretched only a few nanometers thin, about the wavelength of our laser light. If the laser light is not oriented, along the pass-through axis, it is converted into vibrational energy or heat energy in the filter and does not pass through. If it is oriented correctly, it passes through and will strike our fluorophore. Once it hits, the fluorophore will only emit light if there's a good enough absorption dipole along the molecule. Now, this is the important part. The intensity of light emitted is dependent on how parallel the electric field vector of our filtered laser light is to our absorption dipole. If it's perpendicular, you can get no emission of light, but this is rare due to how many molecules will be in the solution. The definition of anisotropy is the angle theta between the absorption vector and the emission vector of our fluorophore. Some molecules will have a higher intensity light simply due to electric field vector perpendicularity, and this is called photoselection. Using some trigonometry, we find the light intensities are given by cosine squared theta for the parallel axis and sine squared phi times sine squared theta for the perpendicular. The electric field created during emission by the fluorophore is given by the Coulomb constant times sine theta over r, and we can square this entire field for the light intensity. Then, when the fluorophore binds to its target, their angular momenta are combined. Big molecules spin slow and small ones fast, which means now our fluorophore, combined with the larger molecule, is rotating slower. This rotational diffusion will displace the emission dipole, and now we can form a relationship between angular momentum, molecular volume, and anisotropy. Add another filter and detector so we can measure the parallel and perpendicular light intensities, where polarization P equals the intensity of parallel light minus the intensity of the perpendicular light, all over the sum of the two. While this is enough information to make meaningful predictions, one of our perpendicular axes is unaccounted for. If we normalize our polarization value with respect to the total emission, it's called anisotropy. To switch between the two easily, let's quickly derive a conversion equation. Much better. Now, we can do some truly groundbreaking biophysics. Viscosity, binding affinity, fluorescent quenching, and more are all derived from this in Francis Perrin's original paper, published in 1966. We understand how fluorescence anisotropy works, but there's one question scientists who develop new medicines frequently need to answer, and that is, does my potential new medicine even bind to its target? And if so, how tightly? We're going to do some simplified calculations to answer this for a mock trial. Again, the whole point of fluorescence anisotropy, with respect to biophysics, is to measure how tightly two molecules will bind to each other. So it goes like this. We have a small fluorescent molecule, a danzyl acid, that is our fluorophore, and we have a larger molecule called bovine serum albumin that is used to help grow cells in a lab. We want to find what their affinity for each other may be. Bovine serum albumin, BSA, has a total of 7 binding sites for fatty acids, and due to the structure of danzyl acids, these sites are where we're going to find our fluorescent probe binds to. We'll need a few polarization values taken from our detector, and we'll also need some known concentrations. First, the polarization value, if we have some concentration of DNS, our danzyl acid, bound to an excessive amount of BSA, much more BSA than we have DNS. Then, the polarization of both compounds, with BSA at some concentration where not all of it is bound. And finally, the polarization of just DNS with no BSA in the solution at all. Let's convert these to anisotropy using our conversion equation. Now, the total anisotropy is given by this equation. The fraction of free fluorophore times its unbound anisotropy, scaled by its quantum yield. Add the same thing, but using values from our bound state. Then divide that by the sum of the products of the free and bound states, and again, each scaled by the quantum yield. If we realize that adding the free and bound state fractions gives us 1, we can do some algebra to obtain a nice simplified form of this equation. Now, all we have to do is plug in to solve for our fractions of free and unbound fluorophore. Scale this ratio by the concentration of BSA, and we have our binding affinity in KDA. A smaller KDA means a higher affinity between the two. Larger KDA means they're not very likely to bind to each other, if at all. Perhaps the two most popular values we can obtain from this technique are the binding affinity between two molecules, as we just solved for, and the molecular volume of our ligand, which is just how big things are. For instance, if there's a cellular membrane too complex to create meaningful images out of, we can use fluorescence anisotropy and molecular volume calculations to help figure out the lay of the land. As for binding affinity, fluorescence anisotropy is often the go-to technique for this. Some scientists use a fluorometer hundreds to thousands of times a year, and it can be heavily automated to save time and cost. Plenty of information exists about this technique and the derivations of how the quantum mechanics and electromagnetic fields play into it. A particularly well-written text, authored by Joseph R. Lakowitz, covers a lot of this, and a link to purchase it is in the description. That's it for this video. Thank you for watching and have a great day. And I don't want else. I don't think you can even really do that to an appreciable degree of accuracy. So the process for animating in 3D is you want to find the crystallographic data for the protein that you're going to be working with. So in my video, I used bovine serum albumin. And so what I'm looking for here, you can literally just go into Google and type in PDB, and that stands for the protein database. And that's where they have a bunch of information stored about all the different kinds of proteins that exist. So you type in PDB and then your protein. And excuse me, this is the first link that shows up. So I click on that. Here it is. This is the 4-letter code that we're looking for right up here. You want to make sure that you have the correct protein, because you might find the same thing but in a different species, and it may be a little bit different, and so you may lose a degree of accuracy with your animation. Not that mine was terribly accurate. There wasn't any like conformation changes when it bound to its target, but if you're going to do something like that and you want to be accurate, you should make sure that you know how to use PDB, and you can blast if you need be, or whatever. So this is just what I'm looking for, the 4-letter code. I'll copy that. And then I'm going to use this program called PyMol. So I already have it imported here, but the way that you can do it, you go to File, Get PDB, and you can literally just type in the 4-letter code right there and hit download. That's all I did to get it to pop up here. The next steps you want to do that I actually should have shown is H stands for hide. So I click H, and here's the hide menu. And you can pick what you want to hide. So I immediately hid waters because there's a few hanging around. If you know a particular sequence that you want to hide, or a particular sequence that you want to show, you can do that as well. I would again go back into the protein data bank and look for what you want. So in this case, I just want the whole thing. So once I have it set up, there's a few different ways you can represent it. Here I picked the surface representation. Here's a ribbon representation. So I'm just going to go back to surface because this is the one that I want to work with. Usually with larger proteins, I think this is the best way to go about it. And you can use some commands in here to get a better resolution for your surface mesh. But sometimes you might actually cut off, you might get some weird geometry. So you're going to have to play around with that. But this was good enough for my animation, so you can go to get it into Blender, which is the 3D program we're going to work with. You just go into File, Export Image as VRML2. And then you can name it whatever you want. I already have it saved, so I'm not going to save it twice. Now I'm going to open up Blender. Here's the default scene you'll see in Blender. For anyone that is new to Blender, it's again, it's a 3D program. You can do all kinds of really intricate model making, lighting, shading. People make video games with this program as well. So it's for animating and video game making. It's a very powerful program, and it is free. So now I'm just going to find where my save is. You know what, rather than do that and search for the file, I'm just going to open up the actual scene that I used to make the video with. And as you can see, it's extremely organized. I keep everything super organized here. Okay. So I'm just giving it a second to load. So you'll hit import, and if you save it the way that I showed you, it should be this one. But as you can see, I'm not very organized at all. I have files all over the place. So I'm not going to go digging around for that. It's going to take me way too long to find it. But you should get an object like this. And then from here, it's a lot of just Blender fundamentals. So it's kind of hard to tell you what you need to do. It depends highly on what kind of molecule you're working with and what concept you want to get through to your viewers. So for BSA, bovine serum albumin, it's reddish. A lot of people here maybe have used it in cell culture, and it's like it's translucent, it's red. So that's the kind of shader that I gave it. And if you go over here to shader editor, yeah, as Kraken says, it's also really viscous. So I tried to give it. It's actually harder than I wanted it to be to see through this, but you can kind of see some light coming through. I maybe should have turned that up a little bit, the translucency, but nonetheless, you can play around with the translucency, pretty much anything you want in Blender, to get the image that you want. I'm not really sure. Does anyone have any particular questions about something that I animated, or about fluorescence and anisotropy in general? I think the hardest part to do, yeah, so the laser was actually one of the most annoying parts to do. So there's several parts to it. So at first I have it just coming out as a beam, where I explain like, oh yeah, we have lasers and they shoot photons, and that's what's going to make our fluorophore fluoresce. But then I explained that it's not just a straight line like this, and you're actually going to see. Oh, I picked the wrong file to open up. But you're actually going to see. It's going to be a sine wave. And so if I had opened up the correct program, these tiny little dots, which you did not see in the video, are actually all emitters. So Blender has this really cool simulation program. It's just called Particles. Okay, quick question. Why is fluorescence anisotropy temperature dependent? Does the orientation of the molecule relative to the detector matter? And so more temperature means more motion, and so scrambles with a higher temperature. Yeah, so anisotropy is in the case of biophysics, it's the angle between the absorption vector and the emission vector. So, oh man, I really should have opened up the correct project. Let me get that going. Oh, this is terrible. You guys get to see how disorganized I am. Oh no. To give you a quick answer, yes. Fluorescence is temperature dependent. Number one, because if you go back to the Jablonski diagram, which is the diagram that shows how energy is handled by the electrons during the whole process, um, the lifetime of a fluorophore is dependent on the temperature, because if you increase the energy, the way fluorescence happens is when it goes back down to a lower molecular orbital. So when it drops, that is when it will spontaneously emit a photon. If it can't drop because you keep feeding energy into the system, then you're actually going to get non-radiative decay, which is heat, and you can start getting phosphorescence. So basically, to give it another quick rundown, it's because you're not letting the electron drop back down to the lower orbital, and that's where fluorescence occurs. Phosphorescence needs spin change. Yeah, I think you're talking about going into a triplet state. And if you keep feeding energy into the system, I believe you're essentially creating more opportunity for that to happen. Again, it's been a while, but I believe that is the reason why. Right, yeah, the forbidden transition. Okay, let me... Oh no. Yeah, this is really terrible. I was so crunched for time at the end of this that it was just all over the place. All right, well, that's unfortunate. Okay, so we're just gonna roll with it. The way I did the laser, I think it was Kraken who asked. So this was actually just to set it up. All I did was this. You need some object to be the emitter, so it's going to shoot out a bunch of simulated particles. So you can pick something. You can just do a cube. So there's my cube. And then now I want it to be an emitter. So this tab right here is called Particle Properties. Hopefully you can see that. And so I'm going to add a new particle system. And as you can see, right now it is acting like a particle emitter, but it's not acting like that laser. So you're going to have to play around with some settings. And the ones that I did here is just like when it starts emitting, when it ends emitting, and the lifetime of the particles that are going to come out. So some of the physics that you can change about it is gravity. So how would you make it a sine wave? So first, let me show you. First, I turned off gravity. And then I gave it a velocity along an axis. And that's just to get them going in a single direction. As you can see, it's still a little bit, it's not what we're looking for. And I don't, Newton will not be happy about turning off the gravity, yes. I'm not going to go through and explain exactly how I made it, but you can quickly keep iterating on this and playing with the settings to get it to go in a straight line. Could try emitting from the volume. But one of the hardest things was actually just to get it to move in a sine wave. Like you saw in the video, I had a bunch of sine waves going. So what I did there was I was actually moving the emitter itself. And the way you do that is, so here is the editor type tab. And you can go into, I believe it's graph editor. And you can hit N to bring up tools. Oh, this might not have been it. I've only done it like a million times. Yeah, I'm just going through, and so I don't know if you missed it, but I had a little video on fluorescence anisotropy, and now I'm going through and explaining a little bit about how I made it. It's strange. There should be a little tab. If you press N right here, it should give you the options to change it depending on a function. Like it should say built-in function, which is, it doesn't tell you that, but it should be a sine wave. Yeah, that was actually my voice. I just edited the crap out of it because my mic is terrible. But yeah, I essentially moved the emitter up and down like a sine wave. You should be able to go into the graph editor like I just did. That's exactly how I did it. Okay, there we go. So you have to turn on keyframing for the position. So here I'm in object properties, and here's the location. And if you see these gray dots, that means it's going to have a single location or rotation or scale for the entire scene. So I'm just turning that on. And now I'm getting the tabs that I want. So I went into modifier, and I hit built-in function. And here it's actually, oh, it does tell you it's a sine wave, and you can pick between cosine, tangent, and other functions. So now you can see our sphere is moving. Okay, I have the rest of the animation playing, but you can see it's moving in a sine wave, and you can change the settings right here. So I obviously wouldn't have it going that fast, but yeah. So then I had the particle in. Let's go back to our cube here. Yeah, so I had the particle emitter coming, it was inside the actual laser. So then I just had it moving back and forth like this. And so I would only do one axis. Here it's bugging out because I haven't assigned anything. But yeah, so that's how I did the sine wave laser. But at first I just showed a simplified version of it, which is just a straight beam, which is not actually how the laser behaves, but it's just to get the concept across. And then the other thing that was kind of a pain, you can actually relate the movements of objects. There's a plugin called Animation Nodes. It's super complicated, and you can get into a lot of like crazy math. Like I actually made a system of cogs, and maybe I don't know if you guys learn this in physics, or maybe some of you guys have taken engineering courses, but you actually can essentially recreate the equation for like how much your cog ratio. So I had like 3 cogs, and it was 6 to 12, and then 12 to 4. Yeah, gears. I forget what that equation is called, but I essentially recreated it in animation nodes. There's a nice tutorial on it, I think. and you can make a bunch of crazy animations with that. But another thing that was sort of a pain to do here was once the laser actually hits the molecule, it stops. So here it's hitting the bovine serum albumin and it's actually stopping. This was a challenge because Blender is actually doing a lot of calculations here for the particle system. You can have the particle system bounce. There's friction. You can have it kind of stick. Trying to find the settings. Here we go. So there's quite a lot of settings that you can mess with here. And the issue is, so now I'm in edit mode. If your model has a lot of polygons, it's going to take a long time to calculate all the possibilities that can happen. And at first I didn't really know how to deal with this because, you know, the protein, when you import it at first, it has way too many polygons. There's like thousands of them. And so when you try and do this particle system, I'm like moving along at 1 to 2 FPS, and it's not possible to work with it like that. So there's actually, in the entire video, you can kind of see them morphing together right here. You can kind of see I have the lower res bovine serum albumin actually directly under the higher res one. And then if we go into our render tab, I just made it invisible. So the particle is actually colliding with the low res bovine serum albumin here. Because if it was colliding with the high res one, it would just take forever to do all the calculations, and they can mess up. So if you're rendering them, if it looks normal when you play it here, it might not actually turn out like that. You can see it's starting to glitch a little bit, and some aren't coming out. Unless you have like a quantum computer to do your rendering, you might run into problems. So you'd have to bake it. But there was a lot of like challenges that I'm not the best at Blender, so it took me a little bit to overcome these. But hopefully, if someone's doing a similar animation, they can use something like this. And then same with the filter. I just used invisible object to cut off particular waves of light. So yeah, any other questions? I guess the other thing I should mention is, so the program, that was my voice in the video. Pretty much all I did was you just highlight the track. In fact, you can use a compressor. I found a plugin online that is a little bit better of a compressor. You want to compress it, normalize, and equalize the voice. Just get out, like my microphone, you can probably hear it now, doesn't pick up bass very well. There's a lot of highs and there's a lot of static. And I managed all that with equalizer settings. So that's how I did that. But yeah, hopefully you learned something about fluorescence anisotropy. Hopefully you learned something about making some animations if you're interested. Maybe you can use it in your projects. But thank you guys for sticking with me and watching. I appreciate it. Yeah, even if you're not making an animation, you can still mess around with Blender and get some cool, just cartoons, just images. Sure. I don't know if anyone recorded this. I don't think so. But I will be uploading the actual video to YouTube, and I'll post a link to that. And if anyone has any questions about animating things in 3D, you can ask me, but there is someone else in the server who recently joined that is probably miles ahead of where I am. Awesome. All right. Thank you. That's it then. Yeah, as I said, if there's any other questions, you can always message me. So thank you, everyone.